In this video, you'll learn how Unicode code points are transformed into binary and why byte ordering could be important if you're a programmer or if you build websites. Image files can store huge amounts of numeric data, so the order of the bytes that make up these numbers is important. Some of these file types store each number with the most significant byte first, and some of them store each number with the least significant byte first. Some are big endian and some are little endian. Knowing the byte order, the endianness of an image file, only really matters if you're developing software to work directly with its contents. But byte order is also important when it comes to text files, including HTML web pages, which are fundamentally text. Text processors and web browsers need to know how to parse a stream of text in order to render it properly. Text characters are usually encoded using one of the Unicode transformation formats. I'll start by talking about how Unicode works. Unicode is a set of numbers called code points that represent pretty much all of the characters you could ever want to use. A code point is like saying the number 69 stands for the capital letter E, or 934 stands for the Greek capital letter Phi. Here are some examples of code points. Code points can be very big numbers, so they're usually expressed in hexadecimal with the prefix U+. Of course, computers work with binary, so code points need to be translated into some sort of binary format. In the early days of digital computing, we could get away with a straight conversion into 7-bit binary because computers worked with a very limited set of characters. The capital letter E, for example, was encoded as 1000101, the number 69 in binary. This encoding was called the American Standard Code for Information Interchange, ASCII. But ASCII could only encode a maximum of 2 to the power 7, that's 128 different characters. To encode the value 934, we need more than 1 byte. In 1991, the International Standards Organization published a new standard called the Universal Character Set. When it was conceived, they thought that 16 bits would be more than enough to encode any character you could ever want, so UCS2 was born. UCS2 was quickly adopted for new technologies of the day, including Microsoft Windows NT and Java. It was called UCS2 because 2 bytes were used to encode each and every character. This allowed for 2 to the power 16, that's 65,536 different characters in total. To state that in hexadecimal, all of the code points between U plus 0000 and U plus FFFF were available. Encoding was a simple matter of converting each code point into regular 16-bit binary. UCS2 was, and still is, capable of representing almost all of the characters in almost every written language in use today. Characters that can be encoded in this way are referred to as the basic multilingual plane. But even while UCS2 was being developed, it was realized that the basic multilingual plane wasn't going to be enough. You can see that the egg emoji can't be encoded with UCS2. In 1996, the Unicode transformation format was introduced. An encoding called UTF-16 promised to address the limitations of UCS2 because it was a variable length encoding that could use either 16 bits or 32 bits. The majority of characters that could be encoded with 16 bits by simply converting the code point into regular binary are encoded in that way. I'll qualify what I mean by the majority of characters in just a moment. You can see that for the capital letter Phi and the Chinese ideograph, the UTF-16 encoding is identical to the UCS2 encoding. Characters that need more than 16 bits are able to use 32 bits instead. A 32-bit encoding in UTF-16 is not, however, a straightforward conversion of the code point into binary. Some of the bit positions are allocated for control bits. The first group of 16 bits is referred to as the high surrogate. and the second group of 16 bits is referred to as the low surrogate. The word surrogate literally means substitute or replacement. To convert the code point for the egg emoji into UTF-16 with 4 bytes, first subtract the hexadecimal value 10000 from the hexadecimal code point. You'll see why you need to subtract this particular value in just a moment. This is usually an easy calculation. Just remove the leading 1. Convert the result into 20-bit binary, because that's how many bits are yet to be assigned. Now, 10 bits can be substituted into each of the surrogates, starting from the right. UTF encodings are often written in hexadecimal, with a pair of hexadecimal digits per byte. The UTF-16 encoding for code point 1F95A can therefore be written as D8 3E DD 5A. Remember, this is just a compact way of writing down the binary digits that were generated from the code point. You may be wondering why 32-bit encodings in UTF-16 need to allocate control bits in the high and low surrogates. Why not just do a straight conversion into 32-bit binary? The answer is actually quite simple. Any software parsing a stream of text encoded with UTF-16 will read 1 bit at a time and assume that each group of 16 bits encodes a single character. But if it sees the leading bit pattern of the high surrogate, it will recognize the start of a 32-bit character. The leading bits of the low surrogate are also fixed to avoid confusion with 16-bit encodings. Needless to say then, the fixed bit patterns at the start of the high and low surrogates are illegal for any characters that require only 16 bits to be encoded. Because of these bit allocations, any 16-bit value in the high surrogate range is unavailable for 16-bit encodings that use regular binary. To state that in hex, any value between D800 and DBFF can't be used. Furthermore, any 16-bit value in the low surrogate range, that's anything between DC00 and DFFF, is also unavailable for 16-bit encodings. In other words, there are no code points in the range D800 to DFFF. This rather peculiar hole in the UTF-16 range of code points can be seen on a number line. It amounts to a total of 2,048 unavailable code points. It's also the case that any code point bigger than FFFF, that's 65,535 in denary, cannot be encoded with 16 bits. Code point 65,536, for example, will need 32 bits instead, and just like the egg emoji, it will be in the high surrogate low surrogate format. Code point 65,536 is 10000 in hex, which is actually a syllabic sign from an ancient Greek script. When encoded with UTF-16, this code point becomes D800 DC00. By the way, the reason for subtracting hexadecimal 10000 in the first step is to generate a new value that can be encoded with no more than 20 bits, and therefore a value that will fit into the surrogate pair format. The designers of UTF-16 wanted to make sure that UCS2 was always a subset of UTF-16. So UCS2 was updated to exclude the same range of code points that UTF-16 excludes. Consequently, these days you can convert from UCS2 to UTF-16 without a problem. You may, however, have problems converting from UTF-16 to UCS2. A completely different Unicode transformation format, which has been around for a long time and is still used on a few Unix-based computers, is UTF-32. UTF-32, also known as UCS4, is very simple. It's just a matter of converting each code point into 32-bit binary. But it's immediately obvious that UTF-32 is a waste of space, so to speak. Some of the most commonly used characters, which need only 1 byte when encoded in ASCII, now require 4 bytes, most of which are nothing but zeros. Even characters in the basic multilingual plane, which is the majority of characters, occupy 4 bytes each, when only 2 are needed. This means text files encoded with UTF-32 can be very large indeed. Nevertheless, streams of UTF-32 text are very easy to process owing to their simplicity. Suppose, for example, you wanted to find the 50th character in a file. Fixed length encoding allows you to simply calculate its position, then access it directly. A variable length character encoding, on the other hand, requires that each character is decoded and examined one after another. UTF-8 is the predominant Unicode transformation format. It deals with the space issue by using a variable number of bytes according to the size of the code point. Similar to UTF-16, it involves fixed bit patterns to indicate how many bytes are being used to encode a character. If a parser sees a byte with a 0 in the leftmost position, it will know it's encountered a character which has been encoded with 1 byte. When the letter E is encoded with UTF-8, for example, it looks exactly the same as it would if it had been encoded with 8-bit ASCII. The same rule applies for all of the original ASCII character set. If, on the other hand, the parser sees 110 at the start of a byte, it knows the character has been encoded with 2 bytes, and it knows that the second byte will start with 10. For example, to encode the Greek capital letter phi in UTF-8, first convert the code point into straight binary. There are 10 bits here, so they'll fit into the 2-byte format. Filling up from the right, drop the bits into position, and pad with zeros in the leftmost byte if necessary. The hexadecimal equivalent of the resulting bit sequence is CEA6. All 3-byte encodings start with 1110 in the leftmost byte. The 2 bytes that follow both start with 10, indicating their continuation bytes. To encode the code point 86CB, employ the same method. First, convert the code point into regular binary. There are 16 bits this time, which will fit into the 3-byte format. And, as before, drop the bits into position, fill up from the right, and pad with zeros on the left if necessary. No padding required here. All 4-byte encodings start with 11110 in the leftmost byte. Continuation bytes start with 10. When the code point for the egg emoji is converted into regular binary, there are 17 bits. Too many to be encoded with just 3 bytes, so the 4-byte format is needed this time. But UTF-8 isn't necessarily the best way to encode text for space efficiency. Here's a comparison of the 3 Unicode transformation formats. Notice that the Chinese ideograph occupies 3 bytes in UTF-8, but only 2 bytes in UTF-16. UTF-8 may well be space efficient for English letters and other ASCII characters, but UTF-16 is better for a great many Asian characters. Despite a long-running campaign for UTF-8 everywhere, UTF-16 is still around. A number of databases, programming languages and operating systems use UTF-16 internally for representing string data. Problems can therefore occur when text files are passed from one system to another. To further complicate matters, when you save a text file in UTF-16 format, you can specify the byte order. Here are most of the characters you've already met, along with their code points and their UTF-16 encodings. And here's a variation of UTF-16 for the same characters. Notice that in the second variation, pairs of bytes are stored in reverse order. One variation of UTF-16 is referred to as big endian, because the most significant byte of each pair is on the left. And the other variation is called little endian, because the least significant byte of each pair is on the left. It's easier to see the difference if you compare the hex columns. Look at the 32-bit encodings of the emojis and you'll notice that only pairs of bytes are reversed, not all four. This is because UTF-16 is designed to be processed 2 bytes at a time. So how does a parser know about the byte order of a file? Let's take a look. Here's Notepad, and you can see I've already input a selection of characters. To get these characters into here, there's a few ways you can do it. You could use the Windows character map if you're using Windows, or if you have a Windows keyboard, you can press the Window key and press a full stop, and this will give you a nice little gadget where you can enter various emojis. If you install one of the language packs, then all kinds of input method editors become available to you, including a rather neat little tool here where you can draw the character and hopefully it'll be recognized. There's even voice recognition. Or an on-screen keyboard you can use. You'll find the emojis on here as well. Whichever method you use is entirely up to you, of course. I just copied and pasted the characters I wanted from a website. I'm going to save this file in UTF-16 format. Notice that the default format is UTF-8, but I can easily change it. There are 2 options here, UTF-16 LE, that's UTF-16 little endian. Let's give the file a name, which I'll recognise later. And I'm going to save it again, but this time in UTF-16 big endian format, UTF-16 BE. And again, I'll change the name of the file so I can recognise which one it is. Now, I want to examine the file data, and I have a very useful little tool here called Hexeditor Neo, which I found online for free. This tool will let me view the encoded data in hexadecimal format. Let's open up the 2 files and view them side by side. I'll just tile the windows so I can compare them. There's a couple of differences to notice. The big endian file starts with FEFF and the little endian file starts with FFFE. Otherwise they are the same except for the byte order. FEFF or FFFE is the byte order mark. This is what any parsing software needs to see in order to determine the byte order. Now I'm just going to make a change to the big endian file. I'm going to change the byte order mark to the little endian byte order mark. So I'm going to confuse the software which is trying to parse this file. If I resave this, it's still a big endian file. The data is still in big endian format, but I've got the wrong byte order mark at the beginning. So if I reopen this file in Notepad, Notepad is going to be confused. It thinks it's a little endian file, but it is actually big endian. So all of the characters are wrong. They've been substituted with something else. Let's put this back the way it was. Reload the file, and it's fixed. UTF-32 can also be big endian or little endian. Notice that the byte order is completely reversed in little endian format because UTF-32 is designed to be processed 4 bytes at a time. This means that UTF-32 text files will normally include a byte order mark, just like UTF-16 files. Is UTF-32 important? A few programmers may need to write code to exchange data with applications that expect UTF-32 encoded characters, but the truth is, UTF-32 is pretty much defunct these days. When it comes to UTF-8, byte order is not an issue. There's only one way that UTF-8 encoding can be done, by design. The leftmost byte of a character must be examined first, because the initial bit sequence indicates how many continuation bytes will follow, and every continuation byte must then start with 10. You cannot simply reverse the byte order, because then it would no longer be UTF-8. All of the encodings would suddenly become illegal, and the data stream would no longer make sense. I'm going to save this file again, but in UTF-8 format this time. Now, you might have noticed there's an option in Notepad to include a byte order mark with UTF-8. This is not a byte order mark as such, because as I've said, you can't change the byte order with UTF-8. Although this so-called byte order mark might help some applications to interpret the data, bear in mind that it isn't standard and it isn't mandatory. Let's compare the encoded data of these two files in NeoHexEditor. They're identical in every respect, except the one that was saved with a byte order mark includes 3 extra bytes at the beginning: EF, BB, BF. Any applications that don't recognise it might attempt to display it with these characters instead. Worse still, an application might try to display it with non-printable characters, so it won't be obvious that the file hasn't been read correctly. There's one more thing I want to show you. I've created a very simple web page in Notepad, and I've cut and pasted a selection of characters into it, some with large code points. I've included the charset meta tag to indicate that I want to use the character set ISO 88591. This will not actually change the encoding. That will depend on how I save the file. The charset meta tag is just a way of letting a browser know what method of encoding was used. ISO 88591 is a single byte fixed length encoding which matches only the first 256 code points of the Unicode character set, the so-called Latin alphabet. ISO 88591 was the default character set for HTML4, so there are a few web pages around that still use it. A similar encoding that you might come across is Windows 1252. In fact, if you save a Microsoft Word document as a web page, it'll be saved with the Windows 1252 encoding. Watch what happens when I encode this file in UTF-8, just by saving it in Notepad's default text format. The browser interprets the encoded data as if it were ISO 88591, and it makes a mess of things. Now, in front of the existing characters, I'm going to specify them again, using special HTML character entities. These numbers are just the base 10 values of the code points. When I save and reload the page, the browser interprets them correctly. By the way, this is how some characters are encoded if you save a Microsoft Word document as a web page. But where I put these HTML character entities has a bearing on what the browser can do. When I place them after the characters I cut and pasted into Notepad, the browser is having trouble again. The heart is broken. Now watch what happens when I save the file without the charset meta tag at all. Modern browsers can detect the encoding automatically. In the name of clarity, it's recommended that you always include the charset meta tag, and that you always specify UTF-8. To summarise, most of the time you don't have to worry about Unicode. It just works. UTF-8 is almost everywhere, and with the potential to encode well over 2 million different characters, it also has some future-proofing built into it. However, an understanding of how Unicode works can help you to track down and fix any problems that occasionally occur as a result of incompatibility between systems. Fancy a challenge? Can you make sense of this UTF-8 data stream? And what would it look like in UTF-16 or UTF-32?